Hi everyone, my name is Mila and today I'll be doing a system design practice exercise. I am doing these to help improve my skill set and hopefully in that process you guys learn something as well. Remember, double check anything you see in here. There are people far more fluent in system design than I am. With that said, if you do enjoy and get something out of my videos, please consider liking, subscribing, and leaving a comment. With that said, let's dive right into our system. Alright, today we'll be designing a ride-sharing service, something very similar to Lyft or Uber, and what we'll be trying to satisfy is CCAPs in the vicinity within an ETA and pricing information, book a cab to a destination and track the location of the driver, see the pickup location of the customer. Drivers can mark trips as complete or cancelled. Customers and drivers can rate the trip after it's completed. And payment processing. Alright, so it looks like we got a lot of things going on here. One of the things we will be doing is definitely using load balancers. And because certain regions and actually certain cities will have really high volume, we'll also capitalize on edge computing. And edge computing is having service centers set up right within a city that is designated for high volume. Generally, data centers are distributed evenly. In this specific case, when you have really high volume cities have a lot of traffic, you want data centers right within those cities to reduce latency as much as possible. For our database, we'll be using Postgres. Now, Postgres is very similar to MySQL. They both adhere to SQL standards. Postgres comes with the benefit of being able to scale easily horizontally and as well as have a lot of extensions that you can use when you're doing geolocations. In this specific case, we could use an extension called PostGIS that helps us with finding two locations, the distance between two locations, and how to get from one place to another place really fast. For tracking the user and driver location so that we have a historical record of it, we'll use a time series database like InfluxDB to store those things. InfluxDB is great. It can handle very large volumes of writes and great for analyzing and analysis later on. Okay, and then obviously our system will be built on an elastic infrastructure like Kubernetes. And with that said, let's dive right into what our data looks like. So we are working with a SQL database, in this case Postgres, so we'll be using tables and columns. Alright, so here we will have, let's start off with a user, and in our user we have user ID. We'll have first name, last name, we will have, let's see, phone, email, password, status ID, and let's do a picture as well, profile picture. And then we'll have a date stamp. And since we have drivers as well, we will have user driver, and if there's a user associated to this table, that means they are a driver themselves. They are a driver. So we will have a user ID, we will have a status ID, and we will have license info and date stamp along other information. Okay, what else we need? Now we need actually a driver can have multiple things, so let's just say user driver license, and then we have user driver license ID, user driver ID. Remember, a driver can go through many licenses and they will need to update those periodically. And then also user driver car, user driver car, and a user ID. The driver will identify the car they use and we'll tie back to the driver. Status ID and then car info, and this is just any number of columns we want. Okay, so now what we need to do is we want user trip, and we will have user trip ID, and we will have user ID and user driver ID. We will have pickup, location, drop off, location. And you know, sometimes there are many other data points you can have here, like total distance and fee. And then we will have a user rating and user driver rating. We can also add a comment in there, but for now, to satisfy what we need to, we're going to do this. And then we will have a transaction, user trip transaction, and this will tie back ID, user trip ID, and then transaction info. This could be many columns, and then status ID. All right. And to make sure that we don't have to always query all the tables to get the rating here, we will simply have an additional, let me just move this up a little. Let's have a rating here and a rating here. These will be calculated and these will be for each specific trip, so we can tie them back to that. Alright, now let's take a look at our API. Alright, this is going to be pretty crazy here. So first we are going to connect to our system, and then as soon as we connect to our system, we are going to be getting information for all the drivers and all the customers. So first thing, we'll do a post, and this would basically be our login. And it really depends on how we're doing this. We could, if we're logging in, we can either do it through an access token if we're going through third party, or if we're doing it locally, we'll just do phone number and password. And so once we get logged, and what we'll get back in return is an access token. We then want to do a get command, do a get request to API. That's let's see. Well, we can say destination, and we will give the longitude and latitude here, and we will get back information about that trip. We can do a post And here, API. Over here, what we will get back is ETA and price and other data. Here we are going to request, once again, long lat. We can actually make this an address. Yeah, it's how you want to process this, right? You could actually do an address where you actually provide an address here. Let's just do this for now, just to keep it aligned with what we're used to. And then here, you will just get a success. And then we will be connected to the database, to our server, and it'll eventually update us with an update and let us know what driver is going to be picking us up with an ETA. See pickup location customer, and then we will post API location. This will be the user's long and lat, and simply a success. This will update the system with your location. And then let's see, we want to do another post, and this one is for rating. And just to be clear, here we are passing, along with this, we are passing our access token as well. Actually, no, we won't be passing our access token because we have a WebSocket connection that's already being authenticated. All right, so rating, you do a rating. Response would be a success or a failure. All right, here, now as a driver, we will do API accept trip, actually request. We will do either accept, reject here. And this will be, we will have a request ID. Could be a trip ID. Actually, let's do a request ID. Actually, it'll be user trip ID. Okay, and success, and maybe if you accept, it will also provide you with other data. Okay, so now we'll do another post, API, and then trip, and we will do cancel. And user trip ID, we don't really need this. This is for, yeah, success, and then yeah. All right, so customer drive complete, post respect, trip cancel, completed. So the client will determine whether you can cancel a trip or complete the trip, and that logic can live within the client itself. Alright, let's make sure we've completed everything here. See pickup location of customers, we've done that. Drivers can mark a trip as complete and cancelled, we've done that. Customers and drivers can rate the trip after it's completed, we've done that. And then payment processing. Okay, so the payment processing would mean that we would need let's see, user payment ID, and then user ID, and then payment info. And this, let's just say this is credit card information for the sake of simplicity. Status ID, and then over here we will use that information and just add user payment ID to let us know what payment was used to pay for a transaction, what credit card was used for to pay a transaction. Okay, and obviously this will also have a date stamp. Okay, let's just make sure we have everything now. Alright, great. I think this satisfies our very basic need. So as always, whenever we have a distributed system, you definitely want to start off with a global load balancer. And in this specific case, because we're going to be using WebSocket connections, what we want to make sure is that our load balancers create sticky connections. That means they're configured to be sticky, meaning that if you disconnect and reconnect to the system, the load balancers will connect you right back to the same server you were previously connected to. That's because sessions could be stateful and regional load balancer, and that information would be lost if you were somewhere else, if you were connected to a different server. Potentially. It would require a lot of overhead to if we were to try to address that in some other fashion. So we will have potentially many load balancers here, and I'll explain everything in a minute. So we have a local load balancer, we have a K8 Kubernetes load balancer, and then for those really high volume locations, we will have edge computing load balancers. Alright, so when you make a request from the global load balancer, when you connect to this server for the first time, your connection is going to hit a global load balancer, and that global load balancer will determine what region is closest to you and has the lowest latency. And in addition to that, it's a safeguard in case if a specific region goes down. Once you hit the regional load balancer, it will then decide how to direct your request. Sometimes it uses round robin, weighted round robin. It can use lowest latency, least process, and many other algorithms. If you're hitting a really large volume area, instead of going to a localized data center to regional load balancer, it will go to an edge computing load balancer. This is a data center that's specific to your location, very in a specific city rather than a general regional location. Otherwise, it'll go directly to a data center that's in your general vicinity and pass on the request to a local load balancer. Now, local load balancers exist within a data center, and they use the same type of approach to direct your requests. It could be it could be round robin, weighted round robin. It could be least latency, least load, any one of those or some other ones that are out there. Once the local load balancer identifies where to go, you basically hit a server, and that server in our specific system will be built on top of Kubernetes. Kubernetes is an elastic infrastructure. It allows us to scale our services up and down based on configuration. And then finally, after that long journey, we are going to hit our API gateway. Alright, we're going to hit our API gateway, and the API gateway is going to decide what to do with your request. Well, the first thing we want to do is make sure that you are authorized. So we will hit an authorization service, and that will validate your credentials. And then once it's determined that your credentials are valid, it will then connect you to a WebSocket service. And now the WebSocket will convert the HTTPS connection to a secure WebSocket connection, where from now on all your requests will be directed directly to the WebSocket rather than hitting the API. Now that we've logged in, we're going to start feeding the system our location. We will be using Redis clusters. Redis is a service that allows you to save information in memory, and having information in memory means we can access them really fast with the lowest latency. And to ensure that we have high availability, low latency, and redundancy, we will be utilizing a Redis cluster. Now, a Redis cluster is a cluster of many Redis servers, and they are all connected and communicating with one another, allowing us to have redundancy and backups in the event one goes down and breaks. In here, we will have the user information, user WebSocket information. User information, WebSocket information, driver information, address information, address data. So all these data, all these particular entities will have their data saved on our Redis clusters. One of the things you do when you are dealing with such a large volume of information, you want to shard your database and Redis servers. That basically means instead of having all your data saved on a single server, which becomes really difficult when you're dealing with really large volumes of data. You split up your servers so that each holds a particular range of information. And what that range looks like and what that data set looks like really depends on the hash key. So you choose a particular key that you will hash your data on, and then you'll use consistent hashing, which is a practice of generating a unique value based on a key you select, so that the information will always go to the same place. There are some trade-offs when you do this. Specifically with related data, you have to ensure that data related to one particular entity is stored in the same server, so that getting related information doesn't become complicated. And anytime you add clusters and additional services, that's additional overhead, additional potential failure points, and cost and complexity. So it's all about managing risks, trade-offs, and gains. So the WebSocket stores that user's connection information in the cache so that it is easily accessible to the rest of the system. Alright, so now we want to make sure we also address our database. So when the authentication service wants to when it wants to verify your information, it will hit the database, but first it will hit the cache to see if your information is there. And if it is, it will validate your session. Alright, so now we're connected to our system. The next thing we need to do is update the location here. So since your system is connected through a WebSocket connection, meaning that communication is constantly going back and forth between the client and the server, we are constantly feeding data from our client to the WebSocket, and then the WebSocket will pass your information on to a location server. Or maybe we can call this tracking service. The tracking service will take your long and latitude. It will update the cache with your latest information, and then it will also write to a message broker. A message broker is a service where you can publish tons of information to, like one particular specific, you generate topics and then you write to those topics information that you want processed by some other service. It's called a message broker. In this particular case, we'll be using Kafka. And once again, we'll have a Kafka cluster here. And Kafka is great because it's got a lot of scalability built into it and allows for global distribution and syncing. So here we will have many topics, and those topics will have specific type of information related to that topic. And here we will have user location topic. So in addition to writing to the cache. It will also publish a message to this topic right here, and then we will have a service down here called store location service that subscribes to this topic and writes that information to our time series DB, which would be location history, and this will be a time series DB influx DB. And what we'll do is do bulk updates rather than each message resulting in a single write. We'll bulk them together and upload them in like hundreds or thousands, whatever that number is. And then later on, business can utilize that information to figure out whatever they want. Over here, we will have our Postgres SQL DB. And here we will have user data, trip, driver, payment information. And just like before, we will be using a cluster and sharding the data accordingly based on our needs and the nature of our data. Alright, so now the next thing we need to do is provide trip data. So we want to provide driver service. Let's call it driver service. And the driver service, let's put that over here, periodically will send information to the client. By getting the data from our Redis server, we know where the drivers are, and the driver service will have a geolocation logic within it to know what drivers to get based on the user's information. So that will provide the details on what drivers are available close to it, close to the customer. And then we want to be able to provide trip detail, trip service. This service will provide information regarding the WebSocket connection will utilize the trip service when an address is sent, and it will use the information in the cache to figure out the distance, and then it will calculate. I'll have some logic to calculate what that fee should be, how long it might be, and it could have live information about the traffic and all that. So, and that's not represented here, but we could have, let's say, a service that contains we could use a third-party vendor that provides information to us about the traffic, so we can take that into account and calculate the time and cost of that trip. So once a trip is started, we will then, let's see here, the trip service will then, also if it doesn't find the data it needs from the cache, it will hit actually no, let me get rid of this. We will have a DB that's specifically designated for address information, address geodata, and this itself hosts SQL plus Postgres. Postgres is an extension that allows us to easily do some geolocation tasks and complex queries that are related to geolocation. So let's see here. We have the ability to log in. We have the ability to get information about a destination. We have the ability to request a driver. We have the ability to see drivers. We are handling the updates of the user and driver's locations. And when we accept or reject, that goes to the trip service. When we cancel or complete, that also goes into the trip service. And now what we need to do is have a rating service. This rating service will post that information. It will handle that request, write it to a topic, once again, this could be the same cluster here, but I'm just trying to make it neat as much as possible. Rating. Oh geez. Why is that happening? And then we will have a service here. Let's call it save rating or publish rating service. And here we will be subscribed to that topic. It will update the database as well as update the cache. Right. And that will take care of that. The last thing we want to do is process the payment. And actually, come to think about it, we would probably, for the sake of simplicity, we'll just have the payments here, but we could have a designated database with sensitive information behind more security protocols. But for now, we will just say we will have a payment service and once the trip is completed, we will process that transaction. We will hit an external third-party service to process our transactions, and then record those let's see here. Actually, let's get rid of this. And once again, we will have another topic here. That the trip service will write to. The payments service will subscribe to, process that information, and then update the database with that latest information. Alright, let's see here. And if the payment fails, it will attempt again. Alright, let's see. Cancel, complete, accept, reject, rating, make payment. Payment would be automatic as soon as the trip is completed. And I think that is my design for ride-sharing service like Uber. Please let me know if I've made any mistake or missed anything. I would really appreciate some feedback. As always, if you did enjoy it, please consider liking my video, subscribing, and most importantly, leaving a comment. Until next time, bye for now.